Hi there. In chemistry, when we learn concepts and topics, they never get lost. We are constantly revisiting old terms and old concepts and learning new things about them. Today, we're going to revisit the idea of boiling point. By definition, boiling point is really a temperature in which a liquid turns into a gas. Sometimes we call boiling point the vaporization point. Regardless of what word we use, it really is just a temperature. To expand its definition now, boiling point is now also the temperature at which vapor pressure is equal to atmospheric pressure on the surface of a liquid. So we're taking this idea of vapor pressure and also atmospheric pressure and kind of mixing it into the boiling point. Now, what happens with vapor and also our atmosphere is that they exert a force. And what happens normally is atmospheric pressure pushes down and vapor pressure pushes up in the simplest idea. When these two pressures are equal to one another, then we actually see boiling. So it's almost like they cancel themselves out. If I have a pressure pushing down and a pressure pushing up, and they eventually cancel themselves out, then they can actually have boiling occur. And that's what we actually see. When we boil water on the stove, the only way for the water to actually boil is if the atmospheric pressure is equal to the vapor pressure. If that's not equal, the water will not boil and it stays a water or it stays a liquid. Now, what happens is our atmospheric pressure actually alters our boiling point. So it is dependent on where we are on the surface of Earth. When we look at this image, we have four different locations. On a plane, which is very high altitude. We have a base camp, we have I guess a camp on the ice caps of the mountain. We have a base camp, and then we also have a camp at sea level. Now, what happens is when we have a high altitude, if we remember this from the last lesson, a high altitude will actually give us a low pressure. And what someone did was they actually went to these locations and tried to boil water. So they wanted to see that the atmospheric pressure was equal to the vapor pressure and then find out what temperature it actually is. When they did this, right, they eventually put it on a graph. So when we look at the first part of a graph, I'm going to draw a rough sketch. This is where the airplane is. The airplane is 20,000 feet above sea level. So it's at a high altitude and it has a relatively low pressure. We notice that at this altitude, the water boils at 79 degrees Celsius. So I'm just kind of rough sketch it. I'm going to make that 79 degrees Celsius and I'm just going to put a point there. Now, halfway down on the ice cap of the mountain, we now have another position in which somebody went there. They went 10,000 feet. I'm just going to write down ice cap here. And then they boiled the water again. When they boiled the water, okay, to watch the water boil, they knew that the atmospheric pressure was equal to the vapor pressure. And they found that temperature to be 90 degrees Celsius. So you start to see a change. They go again, even lower, 6,000 feet above sea level. So we're going to go here. I'm going to call it campsite. And they boil water again. When they boil the water at this position, they find that the water now boils at 93 degrees Celsius. Not a big change, but still different from where it was. So base camp is at 93 degrees Celsius. And then finally at sea level, okay, so I'm going to write down sea level here. They find that the water boils at our normal temperature, since we all live around or on sea level, at 100 degrees Celsius. And when they did this, they created these plots or these points, and then they connected their points in a best fit curve. So they don't actually have to go through each point, kind of go around, and they create a curve. It's not actually a straight line. Now, what this really is just someone doing an experiment where they're changing their altitude and finding the boiling point. Now, in chemistry, someone did the same thing, but they did it for 4 different liquids. And that ends up looking like table H on your reference table. So if you turn to your chemistry reference table, page 4, we now are going to focus on table H. I'm going to explain what you can find on table H, how to read table H, all the different things that are on table H. Before we do so, let me just go back real quick. I want you to know from this picture right here, whenever we boil something at sea level, this is important to us since we almost all live on sea level and we always perform experiments at sea level. You should know that the atmospheric pressure at sea level is equal to the standard pressure. We learned that the other day. Since the atmospheric pressure at sea level is equal to the standard pressure, if we boil anything there, that's normally called the normal boiling point. And it is the normal boiling point. When we boil water and check the thermometer, it is always going to read 100 degrees Celsius for water. So that's what it normally will boil at because we normally live at sea level. But I just want you to recognize that anytime we find a boiling point at sea level, it's called the normal boiling point. We use that as a terminology or a new term. Now, back to table H. Table H has a lot of things, and I want to explain each and every little portion of it just so you know how to read it, and you're going to learn that we can get a lot of information from this. So the first thing to note are really the X and Y labels. You're going to notice that on this graph on table H, we have vapor pressure along the y-axis. I want you to be aware that even though it says vapor pressure, it can really just mean pressure. Because we know that at boiling, vapor pressure is equal to the atmospheric pressure. So you don't always have to remind yourself that it's vapor pressure, you can just assume that it's pressure. Now, this pressure is always in the units of what we call kilopascals. On our x-axis, we have our temperature, and the temperature is always given in degrees Celsius. Now, the scales are important as well. The scales are actually different on the y-axis and also the x-axis. Along the y-axis, every single line represents 10 kilopascals. So your scale is going by 10. Kilo, small k, pascals. However, the x-axis and temperature, each little line, even though it's not labeled, actually represents a scale of 5 degrees Celsius. So I want you to be aware of that they have different scales. So make sure you know how to read it properly. Now, table H doesn't just include water, it actually has 4 different liquids, and we have to be able to compare them, or we're going to compare them. We have something called propanone, which is that first graph here. We have ethanol. We have our water, so we always can compare it to something, and we have something known as ethanoic acid. All right, now before we even start reading the graph, I do want you to recognize that on this graph, there is a line, a dashed line. Let me highlight it for you. Dashed line right here. That dashed line is 101.3 kilopascals. And that number is important to us because 101.3 kilopascals really represents our standard pressure, or if you remember, our sea level. Standard pressure actually means several things. Remember that it can mean 101.3 kilopascals, 1 atm, 760 torr, and 760 millimeters of mercury. So this is actually our standard. This is where we're always going to look for if we want to know what's happening at sea level. Okay, now let's continue with table H. Table H can help us actually find pressure. Whether it's vapor pressure or atmospheric pressure, it doesn't matter. It's going to help us find pressure. So in order to do that, we have to extrapolate information. How this normally works is we are usually given a temperature, and then we have to extrapolate and find the pressure. So watch what happens. If I give you 105 degrees Celsius for water, all I have to do is find 105 right here, and I'm going to go to the curve that has water. So right here. So I'm just going to follow my line or get a ruler, whatever I have to do. I'm going to ignore ethanoic acid and just go to the graph of water. Now, I need to extrapolate information, which means once I hit the curve for water, because that's what I have, I now want to know what pressure this occurs. I want to know what pressure, so I get a straight edge or a ruler, and I run my finger all the way to the y-axis where pressure happens to be. And that now ends up being 120 kilopascals. So by giving you the temperature of water, and then by finding the water curve, I can actually find the now pressure that I would need. So that's the one thing that you can easily extrapolate from this graph. You can use it to your advantage, and you can actually find the pressure of any 4 of these liquids. Okay. In addition to finding pressure, we could also find the boiling point. And that's important. We can find temperature as well. So it works in the opposite direction as well. So if I were given the pressure of 60 kilopascals, so right here, this is 60 kilopascals. So I'm going to given 60 kilopascals, I can actually find the boiling point of any one of these liquids. And we can actually do it for all the liquids. So it works the same way. I'm going to run my straight edge of my finger first to the first graph. By hitting the graph, I now find the boiling point. Because that graph, just like we saw before with the plane and the campsites, really is a graph of boiling point. Once I hit that part of the graph, all I have to do is extrapolate and go downward and hit the x-axis. When I go down, that temperature that I find there for propanone, that boiling point actually ends up being about 42 degrees Celsius. And these are boiling points. Now, I could do this if it only asked for propanone, but I can actually do this for all the graphs. And the reason why I would do it all for the graphs is because I want to explain how this also deals with intermolecular forces. So I'm going to continue on. I'm going to still take the 60 kilopascals, and then I'm going to extrapolate or go all the way to the curve of ethanol. When I go to ethanol and do the same procedure, hit the curve and then drop my finger down to find the temperature, I find now that that temperature is about 66 degrees Celsius. I know it's not perfect, as its boiling point at this pressure. I'm going to keep going. I'm going to go for water, and it's at a low pressure, so water is going to have less than 100. When I extrapolate down for water, I end up getting the boiling point at this pressure for water to be about 87 or so degrees Celsius. And then finally, I'm going to continue on to ethanoic acid. And I'm going to do the same thing. Hit the curve and then drop my finger down to find the temperature. And ethanoic acid ends up being or having a boiling point of about 102 degrees Celsius. Now, the reason why I did all four things, I was given a pressure, I found the boiling point of all four substances, because now that I know that these are boiling points, I can actually make a guess of which one has the weakest intermolecular force and the strongest intermolecular force. We already know that boiling point is an experiment that scientists use to determine which substance has a higher intermolecular force or lower intermolecular force. And according to what we know, that substances that have low boiling points have weak intermolecular forces. So when I compare all four of my substances or my liquids at the same pressure and find their boiling point, I see that propanone actually has the weakest intermolecular forces. It will boil at the lowest temperature. And that means since it boils at that low temperature, I break apart the intermolecular forces easier, since they're so weak, and then I can get the liquid to boil. Now, on the other part of the spectrum, we see that ethanoic acid boils at 102 degrees Celsius. It actually has the highest boiling point. That means it takes a lot of energy in order to break the intermolecular forces and then get the liquid to boil. So ethanoic acid actually has the strongest intermolecular forces of any one of these liquids. And then obviously ethanol and water are in between. But you should know that you can find the intermolecular force when you compare all of them at the same pressure. You need to look at their boiling points. Okay, so now there's a little bit more that I want to teach you about table H, but we're going to isolate one graph. So we're going to just look at the vapor pressure of water. And sometimes when we look at the table H, it kind of gets confusing because there's four liquids on there. So we're just going to isolate water by itself. I'm going to draw a curve of some sort, best one I possibly can. Kind of looks like that, curves up a little. And we're just going to isolate water and just look at water. Now on this curve, I'm going to draw some points on and around it. So I'm going to have A, B, C on the graph itself. I'm going to have point D here and also E up there. I'm also going to put a point in front of the curve. That's going to be point F, and also behind the curve. And this is why I eliminated the other curves for propanoic acid, sorry, not propanoic acid, for propanone, ethanol, and ethanoic acid, just so we can look at the points. Now, here's the thing to notice about these points. When looking at points A, B, C, D, and E, these all represent boiling points, because the curve really is just a curve of boiling points. But it is the boiling points specifically at different pressures. And that's fine, because we know that at different pressures, water or any liquid will boil at a different temperature. I want to make sure you understand that point D is very specific. Since point D is on the line of 101.3 kilopascals, which is our sea level, point D is special. We call it the normal boiling point. Any boiling point at 101.3 kilopascals is known as the normal boiling point, and we use that word normal. All right, because 101.3 kilopascals is standard pressure or our sea level. Now, let's focus on the ones that are not on the line. F. Point F is in front of the line for boiling. So point F, let's kind of pretend for a second, is at a temperature of 50 degrees Celsius. We can say that normal boiling point for water is at 100 degrees Celsius. That part's easy. And while we're at it, since we're going to talk about it eventually, G, we can say is at 120 degrees Celsius. Now let's focus on point F. point F is at 50 degrees Celsius. However, the boiling point or the normal boiling point for water happens to be 100 degrees Celsius. So when we look at this pressure and this temperature, exactly at this point right here, we see that this substance is mostly a liquid. There is some evaporated liquid above the surface, but it's going to be mostly a liquid. It hasn't reached its vaporization point. It hasn't changed phases completely. Okay. Point D we already know is the normal boiling point. So this is where we're going to see a phase change from our liquid to our gas. We already know that point. But also point G. Point G is after the boiling point. It's at about 120 degrees Celsius. Since point G is above the boiling point, we see in this point that it is mostly going to be a vapor because the phase change has already occurred. And now we're moving in that direction, so it's boiling, boiling, boiling. So it's going to be mostly a vapor, and there's going to be some liquid. Okay? When looking at the graph, you have to pay attention to the points and be careful. Sometimes it gets confusing with the 4 liquids on there. All right, so today you're going to try some questions on your own using Table H. So if you don't have Table H, get a copy or use a digital copy. That's it for now. I'll see you in the next lesson.